Magic angle graphene uses faint light to transform an insulator into a metal, revealing a new way to make the unseen visible. Tim McMillan, August 11, 2026. A material that normally blocks the flow of electricity can suddenly begin behaving like a metal when exposed to remarkably weak light, according to a new experiment involving one of the strangest forms of graphene ever created. The breakthrough reveals that an unusual quantum effect could eventually provide a new way to detect some of the faintest radiation around us. Researchers working with magic angle twisted bilayer graphene found that faint, long wavelength radiation can effectively melt the material's fragile correlated insulating state, causing its electrical resistance to plummet. Remarkably, the experiments showed that even relatively weak radiation could trigger a dramatic transition from an insulator to a metal. Beyond revealing an unusual way that light can manipulate matter, the discovery could provide the foundation for extremely sensitive detectors capable of spotting faint terahertz and far-infrared radiation. With further development, detectors operating at these wavelengths could have applications ranging from security imaging and material inspection to astronomy and environmental sensing. The study, published in Nature Communications, centers on magic angle twisted bilayer graphene, or matbij, a material produced by stacking two sheets of graphene and rotating them relative to one another at a carefully controlled angle. Under the right conditions, interactions between electrons can cause magic angle graphene to enter exotic collective states, including superconducting and insulating phases. Here we show that this expectation does not apply to magic angle twisted bilayer graphene matbij and demonstrate giant photoresponse of matbij to low-intensity long-wavelength photons when it is tuned to half-filling of the Moire band, researchers write. Far-infrared photons selectively overheat the low-heat capacity electronic subsystem, driving a collapse of the correlated order and producing a giant photoresistive response. Ordinarily, changing an insulator into a conductor with light requires supplying enough energy to alter how electrons can move through the material fundamentally. Previous experiments involving light-induced insulator-to-metal transitions have frequently depended on intense, ultra-fast excitation. Magic angle graphene offers another route. Twisting graphene sheets at carefully controlled angles creates a larger repeating structure known as a Moire superlattice, dramatically changing how electrons within the material interact. Those interactions have already produced some remarkable results. As the debrief reported last year, researchers studying magic angle twisted trill-air graphene uncovered new evidence of unconventional superconductivity, including unusually tightly bound electron pairs and a distinctive superconducting energy gap. That work was part of a greater effort to understand whether these exotic materials could eventually help scientists design superconductors capable of operating at much higher temperatures. In the new study, researchers exploited another unusual state that can emerge in magic angle graphene. At certain electron densities, interactions between electrons become unusually important, allowing them to organize into what physicists call a correlated insulator. That collective state is extremely fragile. The correlated insulating gap exists at an energy scale of only a few millielectron volts. Previous measurements cited by the researchers indicate that a gap of approximately 1 millielectron volt at very low temperatures gradually closes as the material warms and disappears around 10 Kelvin. The researchers realized that weakness could become an advantage. Their experimental device consisted of magic angle graphene sandwiched between layers of hexagonal boron nitride and configured as a field effect transistor. A graphite backgate allowed them to precisely control the number of charge carriers and tune the graphene into its correlated insulating state. They then exposed it to millimeter wave and far-infrared radiation. Instead of needing to inject large numbers of charge carriers, the incoming photons heated the graphene's low-heat capacity electronic system. That relatively small temperature increase was enough to destabilize the cooperative electronic order, retaining the insulating state. The gap collapsed, resistance dropped dramatically, and the material became metallic. Measurements in darkness and under illumination reinforced that interpretation. Without radiation, the graphene displayed the temperature-sensitive resistance expected from an insulator. Under millimeter wave illumination, it instead exhibited behavior representative of a metal. Researchers compare the mechanism to superconducting bolometers, highly sensitive radiation detectors in which incoming energy interrupts a superconducting state. But their graphene device essentially operates in reverse. Instead of destroying a zero-resistance state, approaching photons destroy a high-resistance correlated insulating state and turn it metallic. That makes the insulator-to-metal transition more than an unusual demonstration of quantum physics. It becomes the detector's signal. The team found that the device responded across wavelengths ranging from 85 to 2140 micrometers, encompassing far-infrared and millimeter wave radiation. That portion of the electromagnetic spectrum is particularly interesting because it can reveal things ordinary cameras cannot. Terahertz radiation can penetrate some materials opaque to visible light, while interactions between this radiation and matter can provide information about a material's composition. More capable detectors could therefore eventually contribute to technologies such as security scanners looking for concealed objects, systems inspecting manufactured components without cutting them open, or sensors identifying substances using characteristic spectral markers. Astronomy offers another potential application. Cold dust, star-forming regions, and other objects that may be faint or obscured at visible wavelengths emit radiation in the far infrared. Detecting those extremely weak signals requires exceptionally sensitive instruments, making improved detector technology valuable for future astronomical observatories. The experimental graphene detector exhibited considerable intrinsic sensitivity. The researchers measured an internal voltage responsivity of approximately 17 million volts per watt of absorbed power. They note that its internal responsivity exceeds that of many commercial bolometers operating in the same spectral region. However, researchers caution that practical external performance is presently limited partly by how efficiently radiation is absorbed, meaning the experimental device is not equivalent to a finished commercial detector. Better antennas, cavities, metamaterials, or other structures designed to funnel radiation into the graphene could potentially improve its performance considerably. There are other hurdles. The effect currently requires ultra-low temperatures, and the unusually strong response depends upon generating high-quality magic angle graphene structures. Those requirements mean practical security scanners or telescope cameras based on the technology remain prospective rather than imminent. Still, there are encouraging characteristics. The photoresponse persisted at temperatures around 6 to 7 Kelvin and remained robust in magnetic fields of several Tesla, with substantial reduction appearing only above roughly 4 Tesla. That magnetic field tolerance could make the technology attractive for specialized scientific instruments where superconducting detectors may meet limitations. The current device also has an estimated practical response time of roughly 50 nanoseconds, largely because of its electrical design. The underlying electron cooling occurs much faster, and researchers estimate that smaller devices could reduce that practical limit by at least an order of magnitude. They also envision twisted multilayer materials, wafer-scale growth, and large-format detector arrays as potential directions for future development. For now, the experiment demonstrates that in certain quantum materials, changing electrical behavior does not necessarily require pumping large amounts of energy into individual electrons. Sometimes, a small amount of light only needs to destabilize the collective state that those electrons have constructed together. For physicists, the discovery offers a new way to investigate how fragile collective states of matter collapse and recover. For engineers, that same fragility could become useful precisely because extraordinarily weak radiation can trigger an extraordinarily large electrical response. Our experiments can be further generalized for time domain interrogation of the CI state itself, researchers write. Radiation-driven excitation confined within the flat band, combined with time-resolved monitoring of the CI photoresistance, would allow direct access to the intrinsic timescale of correlated order suppression and recovery, thereby probing the collective dynamics within the ground state. Study, Eliason, L. Shalov, A. L. Kravtsov, M. et al. Correlated Insulator Moire Bolometer. Nature Communications 2026.